Hello everyone, this is going to be part 5 through 8 of the practice exam solutions. Okay, let's look at part 5, which is sets and operations on sets, and there will be one question like this on the real exam. Okay, so here we have A is 146, B 2346, C is 256, and then we have the universal set is all numbers from 1 to 7, and we just have a bunch of different things that we need to find here. So let's just go ahead and do these. Okay, so part 1 is A minus C intersected with B complement. So I'm just going to substitute in the different parts here, and then I'll work on them. So I'm substituting in A and C and B complement. Okay, and so I'm going to work on the part in the parentheses first. So the set 146 minus 256. So you take everything in 146 and then you delete anything that was in 256. So basically I'm only going to be deleting the 6. Okay, so this is going to be 1, 4. So I delete the 6. So that deletes. And then I'm going to have this intersection here, and now let me go ahead and do the complement. So the complement of the set containing 2, 3, 4, 6 is going to be everything that's in the universe and not in 2, 3, 4, 6. So basically everything in 1, 2, 3, 4, 5, 6, 7 that is not 2, 3, 4, or 6. And so this is going to leave me with, I'm going to have 1, I'm going to have 5, and I'm going to have 7. Okay, so now that I'm down to this point, I'm just doing an intersection of the set 1, 4 with the set 1, 5, 7. So that is everything that's in the overlap. Remember, when you have the intersection of two roads, that's where they overlap at. So the intersection is the overlap. So this is just going to be 1. Okay, number 2. So I'm doing A, which is 1, 4, 6, crossed with, so Cartesian product with, the complement of B, which I just found the complement of B, so this is not too bad. Okay, so let me go ahead and do the complement, and then I will do the Cartesian product. So the complement of B, everything that is not in B, but is in the universal set. Again, that's just 1, 5, 7. Okay, so now what I have to do is I have to list all of the ordered pairs, where the first thing in the ordered pair comes from the first set, and the second thing in the ordered pair comes from the second set. So you just want to be really systematic when you do this. So first I'm going to do all the ones that start with 1, and there's going to be 3 of those. Okay, and those are going to be, so I'm going to use the sets in the second set there, which is 1, 5, 7. So this is going to be 1, 5, 7. Okay, then I'm going to do all the ones that start with 4, so that'll be 4 and 1. And then 4 and 5, and then 4 and 7, and then all the ones that start with 6, so this is going to be 6 and 1, 6 and 5, and 6 and 7. And that's it. So if you have 3 things in the first set and 3 things in the second set, you're going to have 9 things in your Cartesian product. Okay, part 3. So B complement again, which I know how to do, and then C union A. Okay, so let me write out, let me just substitute in all the different little pieces and parts for A, B, and C, and then I will perform the operations. So C is going to be 2, 5, 6, and then union with A, which is 1, 4, 6. Okay, so I know how to do B complement. That is just 1, 5, 7. So things that are not in B but are in the universal set. And now I have an intersection. And now let me simplify the part that was in the parentheses. So C union with A, that's everything that's in C or in A. So you basically just smoosh C and A's sets together into one big set. So you want to think of union as being like marriage. C and A are getting married. They're going to share all their stuff. So everything that's in either C or in A. So let's see, I'm going to keep everything from C, so I'll just write all the stuff from C down first. And then I'm going to add in anything from A that I didn't already write down. So I'm going to get a 1, and I'm going to get, let's see, a 4, and then I already had the 6. Oops, this is a typo here. Okay, so now I'm just doing the intersection of these two sets. So everything that's in the overlap of these two sets that are remaining here. So what is in both of them? They both have a 1. They both have a 5. They don't both have a 7. They don't both have a 6. And they don't both have a 4. So I believe that's it. So just 1 and 5. Okay, so number 4. So the union of A with B complement again. I guess I did a lot of B complements, didn't I? Okay, so A is 1, 4, 6. And then B complement, so that's going to be 2, 3, 4, 6 complement. So I'll do B's complement first. Okay, so the complement of B is again just 1, 5, 7. Sorry, that really doesn't look like a curly brace. Okay, that's a little better. All right, so now the union of these two things, so we're just going to smoosh them together, everything that was in the first one or in the second one. So I'm just going to write the first one again, 1, 4, 6, and then I'll add in anything that was in the second that I didn't already put. So that's going to be 5 and 7, and then I already had the 1. Okay, that's it. I'll go to the next slide for the rest. Okay, so number 5. So A cross C minus B. Okay, so I'll just fill in all the little pieces and parts again. Cross, and then C is 2, 5, 6, and then minus, and B is 2, 3, 4, 6. Okay, so I'm going to do the part in parentheses first, the minus. So 1, 4, 6 will stay the same, and Cartesian product. Okay, so the minus, so I'm going to take everything in 2, 5, 6, and I'm going to take away anything that was in 2, 3, 4, 6. Okay, so the 2 is going to be taken away, the 5 is going to stay, and the 6 is going to be taken away. So that's going to leave me only the 5. Okay, so that makes this Cartesian product pretty easy. So this is the set of all ordered pairs where the first thing is in the first set and the second thing is in the second set. So they all have to end with 5, and then they can either start with 1, 4, or 6. Okay, so I just get those 3 ordered pairs. All right, number 6, so I'm doing the power set. I put it in parentheses that it was the power set because I couldn't quite make the same script P that was in the textbook. So this is the power set of A minus C. So let me do the A minus C part first. So that's going to be 1, 4, 6, minus 2, 5, 6. So I'm going to take away anything in 1, 4, 6 that was in 2, 5, 6. So I'm going to take away the 6. So this is going to be a power set of just 1 and 4. So just to remind you, the power set, that is the set of all possible subsets of the set. Okay, and you want to list them off systematically, starting with the smallest. So the smallest possible subset of the set containing 1, 4 is the empty set. And then we can have sets with just 1 element each. So there's 1, and there's 4. And then we can have the set with 2 elements, which is the whole thing, 1, 4. And once you've gotten up to the largest possible set, which is the original set, then you're done. So that's all the possible subsets of the set containing 1, 4. Okay, number 7, A minus C intersected with B. So we just did A minus C, so that part's not too bad. So this is 1, 4, 6, minus 2, 5, 6, and then intersected with B, which is 2, 3, 4, 6. Okay, so I'll do the parentheses part first. So I'm taking away anything, so I'm starting with 1, 4, 6, and I'm taking away anything from 2, 5, 6. So that's going to get rid of the 6. So I'm just going to have 1, 4. And then I'm intersecting that with 2, 3, 4, 6. So remember the intersection, that is the overlap. So anything that's in both of those sets, and I think it's just 4. Okay, number 8. So we're doing the power set of B complement. So B complement is going to be 2, 3, 4, 6 complement. Oops. Okay, so the complement of that, oops, I'm doing typos all over the place. Okay, so the power set of, so the complement of B is everything in the universal set that is not in B. So that's 1, 5, and 7. Okay, so now I'm doing the power set of 1, 5, 7, so that is the set of all subsets. So the smallest subset would be the empty set, and then we can have the next smallest would be each element by itself. And then the next smallest would be 2 elements at a time, so we could have 1, 5, or we could have 1, 7, or we could have 5, 7. And then finally, the largest subset we could have would be the entire original set, which is 1, 5, 7. These curly braces are really devolving. Okay, and that's it. All right, number 9. So number 9, A complement union C minus B. So I'll just fill in all my little pieces and parts. This is 1, 4, 6. Complement union with C is 2, 5, 6 minus B is 2, 3, 4, 6. Okay, so first I'm going to do the part in parentheses, and I can also do the complement now. So the complement of A is everything that's in the universal set that is not in A. So the universal set is 1, 2, 3, 4, 5, 6, 7. And the ones of those that are not in 1, 4, 6 is 2, 3, 5, and 7. So that is A complement. And then I'll do the parentheses part. So I'm going to take everything in 2, 5, 6, and I'm going to take away everything that was in 2, 3, 4, 6. So I'm going to take away the 2, I'm going to take away the 6. So that's just going to leave me with 5. And I don't really need these parentheses here. Okay, so now I'm doing the union of 2, 3, 5, 7 with 5, and so I'm just going to smoosh those two together, but 5 is already in the first one, so this is just going to be 2, 3, 5, 7. Okay. And finally, I'm going to squish number 10 at the bottom here. So number 10, C minus B union with A. So let me just fill in all these parts here. So this is 2, 5, 6 minus 2, 3, 4, 6, and then union with A, 1, 4, 6. Okay, so let me do the part in the parentheses. So I'm starting with 2, 5, 6, and I'm taking away 2, 3, 4, 6, so that's going to take away my 2 and my 6, and that's just going to leave me with the 5. Okay, and then I'm unioning that with 1, 4, 6, so I'm just, this is just the set containing anything that was in 5 or in 1, 4, 6. So it's going to be 5, 1, 4, 6. Okay, that's it. All right, let's look at part 6, which is function basics, and there will be one question similar to this on the real exam. Okay, so for number 1 here, we just have to answer these questions for the function that's shown, and it's a little function diagram. I tend to think these are personally pretty straightforward, so I hope you agree. All right, so let's do part A. So the function, we can see here from the diagram that the domain is the set A, which consists of the elements 4, 6, 8, and 10. So that's the domain. Part B, the codomain. So the codomain is that whole set that's on the right, regardless of whether the elements were actually reached or not. So the codomain is B, which is P, Q, R, S, and T. Okay, part C, the range. So the range is actually only the elements that are outputs of the function. So the range is only going to be the ones that the arrows go to. So that's going to be Q and T. Okay, part D. What is f of 8? So f of 8, you just follow the arrow from 8 and it goes to T. So that's T. Okay, part E. what is f of 6, 8, the set containing 6, 8? So for that, you just want to look at where both 6 and 8 went to, and just use that, and then write it as a set. Okay, so this is going to be, so basically it's the set containing f of 6 and f of 8. So that's going to be Q and T. Okay, and then for the next one, part F, what is F inverse of the set containing Q? Or in other words, what is the inverse image of the set containing Q? So for this, you want to look backwards from Q. So you want to look back from Q to wherever Q came from. Okay, so along these lines here. So Q could have come from 4 or from 6 or from 10. So the inverse image of the set containing Q is going to be those 3 elements in the domain, 4, 6, and 10, that all map to Q. Does that make sense? I hope. Okay, so part G, is F 1-to-1? So 1-to-1 means that different inputs always have different outputs. Or another way to say it is that any output only has one input. Okay, so if you get the same output, then you must have had the same input. But this is definitely not the case, because, for example, f of 4 and f of 6 are the same, which is not something that would happen if it were 1-to-1. Okay, so for H, onto, so onto means that you hit every element in the codomain, which is definitely not true. So for example, P, R, and S are never reached. Okay, and then finally for part I, if either of your answers to G or H was no, then this is also going to be a no, because a 1-to-1 correspondence is a function that is both 1-to-1 and onto. So that's a no. All right, so let's look at the second one here. So it's exactly the same questions, just a different function. So part A, the domain is going to be capital P, which consists of A, B, C, and D. Part B, the codomain, is capital Q, which consists of 1, 2, 3, and 4. Part C, the range. So that's only the elements that you actually hit, but that is in fact everything, so it's all of Q. So 1, 2, 3, and 4 again. Part D, what is G of B? So you just follow the arrow from B to 1, so that's 1. Part E, so G of the set containing C and D. So again, that's just the set containing the image of C and the image of D. So the output for C is 2, and then the output for D is 4, so that's 2 and 4. Okay, and then part F, what is the inverse image of the set containing 1 and 2? So what you want to answer here is all of the elements that would either produce 1 or 2. Okay, so the element that produces 1 is going to come from B. So you just look along that arrow from B to 1 and you get B. And then the element that produces 2 is going to be C. So you're just looking back from 2 to C. So that's that. And then part G, is G 1-to-1? So in this case, yes, every input produces a different output. We don't have any arrow heads touching the same dot on the right. Okay, so every arrow goes to a different output. So this is yes. And then part H, is G onto? And again, this is yes. We did reach everything in the codomain with an arrow. And then so for part I, since we got yes and yes, this will also be a yes. It is a 1-to-1 correspondence. Okay, number 3, same questions. So part A, the domain. So the domain is that big blob on the left, which is called V, and that consists of I, J, K, and N. Part B, the codomain, that is the blob on the right, and that is W, which is just P, Q, and T. Okay, part C, what is the range of H? So the range is everything that you hit with the arrows, and that is, in this case, it's everything. So that's all of W. Okay, part D, what is H of J? So you just follow the arrow from J over to Q. Part E, what is H of the set containing J and K? So you're looking at what arrows go from J and also from K, and then you answer as a set. So that is going to be Q and T. Part F, what is H inverse, or the inverse image of Q and T, that set? So this time you're looking back along all of the arrows that went to either Q or to T. So this is going to give us J and K and also N. So J goes to Q, K goes to T, and N goes to Q. So that is F. Part G, is H 1 to 1? So this is going to be a no, and the reason there is because H of J is the same as H of N. So J and N are two different elements, but they have the same output, so that's not allowed. Onto, yes, this is onto. We did hit everything in the codomain. And then part I, this is going to be no, because we got a no for part G. Okay, let's look at part 7, which is equivalence relations, and there will be one question similar to this on the real exam. Okay, so let's look at number 1 here. We have to prove that this is an equivalence relation. So E is the relation defined on the integers as follows. For all m and n in the integers, m is related to n by E, if and only if 2 divides m minus n. Okay, so let's go through the things we need to prove here. So the first one is we have to prove that this is reflexive. Okay, so that means that every element is related to itself. Okay, so what we're going to do is we're going to take an element from the set that this relation is on. So we'll just call it M. So let M be in Z, and we need to show, you don't have to write this in yours, but we need to show that M is related to itself by E, like this. Okay, so let's see, what do we know about M? So I need to show that M minus M is divisible by 2. So M minus M is 0, and 0 is divisible by 2 because it equals 2 times 0, which is an integer. So this is true. M is related to itself by E. All right, so that was pretty easy. Now let's do the symmetric property. So symmetric, I'm going to need to take 2 elements from the underlying set. So I'll call them M and N. And what we're going to do is, well, let me show it like this. So we will show that if M is related by E to N, then N is related by E to M in the other order, like that. So we're trying to show an if-then statement. That means we're going to need to do a direct proof. So I'm going to assume the if part, and then I'm going to show the then part. So let's suppose that M is related to N by E. All right, and what do I get from that supposition? So that supposition tells me that means that 2 divides M minus N. Okay, so that means that M minus N equals a multiple of 2. I'll say it equals 2 times K for some integer K. This is just the same as saying there exists some K such that M minus N equals 2K. Okay, so then what is N minus M? So then N minus M, isn't that just the negative of M minus N? So isn't this just negative 2K? Or in other words, 2 times negative K. All right, then since negative K is also an integer, this shows that 2 divides N minus M. So N is related by E to M in the opposite order, like that. Okay, so this does have the symmetric property. And then finally we need to show the transitive property. So for this one I need 3 letters, so I'm going to let M n and I don't know, L be in the integers. Okay, and now we will show the following. So we will show that, and again, you can leave this parentheses part out, but I'm just trying to give you the idea of what we're going to do here. So if m is related to n by e, and m is related, oh, sorry, not m. If n is related by e to L, then we can sort of transit between m and L along that little chain there. So m would be related by e to L, like that. So that's what we need to show, and it's an if-then statement, so we're going to do it with a direct proof. So we'll assume or suppose or let m be related to n by e, and n be related by e to L, and then we're going to try to show that m is related to L by e. So what do we get from this assumption here? Okay, this means that 2 divides m minus n, and also 2 divides n minus L. Okay, so, well, what can we do then? If these are both divisible by 2, then m minus n equals 2 times k for some integer k. And likewise, for the other one, n minus L equals, I have to use a different letter now, so I'll call it I. 2 times I for some I integer. Okay, now how am I going to get m minus L? So I think I can actually just add those two equations together and get m minus L. So m minus n plus n minus L equals m minus L. So m minus L is going to equal 2k plus 2i, right? That's what I get from adding those two together. Okay, and that is going to be a multiple of 2 because I can just factor a 2 out of it. So now I just need to argue that that means that 2 divides m minus L. So since k plus I is an integer, this means 2 divides m minus L. So m is related by e to L. All right, and that's what I needed to show. So at this point, I've shown all 3 properties, and I'm done. Okay, let's look at another one. This one is actually quite similar. So C is the relation defined on the integers as follows. For all a and b in the integers, a is related to b by c, if and only if 5 divides a cubed minus b cubed. Okay, so let's go ahead and start with the reflexive property. So for reflexive, I'm going to take one element in the underlying set. So let a be an element of C, and then I'm going to show that a is related to itself. So in order to do that, I'm plugging it into the definition there for both a and b. So I need to show a cubed minus a cubed is divisible by 5. So that is not very hard because a cubed minus a cubed is 0, and 5 does divide 0. All the integers divide 0. So this means that a is related to itself by c. Okay, so that's reflexive. And now the symmetric property. So for this one, I need to let there be 2 integers. So I'll call them a and b. And I'm going to suppose that they are related to each other in the first order. So suppose a is related to b by c like that. And then I'm going to show that b is also related by c to a. So this assumption here means that 5 divides a cubed minus b cubed, like that. Okay, so a cubed minus b cubed equals 5 times some integer, which I'll just call I, where I is an integer. I should have said some I and z. Let me just erase it. Putting the for some I and z part at the end there is the same as putting then there exists some I and z at the beginning. Yeah, so then what is b cubed minus a cubed? So that's what I need to find in order to show that b is related to a by c. Okay, so then b cubed minus a cubed is just going to be negative 5i, or I can take a 5 out of that and put the negative I in parentheses. Okay, and then I can say that since negative I is an integer, this shows that 5 divides b cubed minus a cubed. So that means that b is related by c to a. Okay, so that's the symmetric property. And then for the transitive property, you need to take 3 elements. So I'll call them, well, I don't really want to use C because I'm already using C for something else, and I don't think I can write it differently enough, so I'm going to call them A, B, and D. So let A, B, and D be in the integers. And now I'm going to suppose that A is related to B and that B is related to D. So A is related by C to B, and that's not a D, sorry. And B is related by C to D. And I'm going to try to show that A is related to D. Okay, so since A is related to B, that means that 5 divides A cubed minus B cubed. So there exists some integer, which I'll just call k, I guess. So there exists some integer k such that A cubed minus B cubed equals 5k. And then I'll do the same thing for the relationship between B and C. So since B is related to D by C, there exists some integer, which I'll just call j, I guess, such that B cubed minus D cubed equals 5 times j. Okay, so that's what it means to be divisible by 5. Oops, I left that part out, didn't I? Sorry, I skipped right to the end of it. Let me go back. Oops. Okay, so that means, okay, so since B is related to D by C, that means that 5 divides B cubed minus D cubed, and then that means, so there exists some integer, which I'll call j, such that B cubed minus D cubed equals 5j. I mean, you could just skip right to that, it's fine, but I just wanted to put in the intermediate part so you understand it better, I hope. Okay, so then how are we going to get A cubed minus D cubed? So again, we can just add the equations together. So then by adding the equations, we get A cubed minus B cubed plus B cubed minus D cubed is going to equal 5k plus 5j. So here the B cubed and the negative B cubed cancel out. And then we can also factor out a 5 here to get k plus j. Okay, so since k plus j is an integer, this shows that 5 divides A cubed minus D cubed. So that means that A is related by C to D, and that's what we needed to show for the transitive property. Okay, so that one's done. All right, let's look at the last one. So this time the elements in our set are ordered pairs, so it's a little bit tricky maybe. And then the thing that is making 2 ordered pairs equivalent is if their first coordinates are the same. All right, so let's give this a try. So first for reflexive, I'm going to take one element from the underlying set, but remember the underlying set here is R cross R, so my element is going to look like an ordered pair. So I'm going to say let Wx be in R cross R. Okay, then I'm going to show that Wx is related to itself. So how am I going to do that? I want to show that W that has the same coordinate, Wx and Wx have the same first coordinate is what I'm trying to say. So then W equals W, so W comma X will be related by L to W comma X. So it's not very hard, it's pretty obvious. All right, let's do the symmetric one. Okay, so now I'm going to take two ordered pairs. So I'm going to let Wx and YZ be in the reals cross the reals. So that's all ordered pairs of real numbers. And now I'm going to suppose that these two are related to each other by L. So I'm going to suppose that Wx is related by L to x, or sorry, to YZ. Okay, and now I want to try to show it in the other order so that YZ is related to WX. So what do I get from this supposition? Then this tells me that W must equal Y. Well, since W equals Y, Y also equals W, so I can just do these in the other order. So I can put the YZ here, and then put the WX on the other side. Okay, so that was pretty easy. And then finally, let's do the transitive. So I'm going to need three ordered pairs this time. So let's see, I'll do, I guess I'll start with UV, and then WX, and then YZ. So they're all in alphabetical order. Okay, and now we're going to suppose that these are all related in a little chain. So UV is related to WX, and WX is related to YZ. Okay, so then what do I have? So UV is related to WX, that means that U has to equal W, and WX is related to YZ, so that means that W has to equal Y. So then I can use the transitive property of equality to say that U must equal Y. So then from there I can say that UV is related to YZ, which is what I need for transitivity. So actually this one was the easiest one, even though it's a little bit complicated with the ordered pairs. Okay, so now let's look at part 8, which is partial orders and Hasse diagrams. So all you're going to have to do on these questions is just draw a Hasse diagram. So the partial order here is, we're giving it by this little symbol here, the less than or equal curvy symbol. So the underlying set that we're going to do our Hasse diagram from is these subsets here, and the partial order relation is actually the subset relation. So we're just going to put the one that is a subset of most of the other ones at the bottom, and I think the empty set is a subset of everything, right? So that is going to go at the bottom. And then the next thing, what is something that contains that as a subset and doesn't contain any of the others? So it makes sense to go just to the next smallest set. So if I have the set just containing A, that will contain the empty set as a subset. So I'm going to have an arrow that goes up from the empty set to that set that just contains A. And then, so I've taken care of that one, and then for B, that also contains the empty set as a subset. So I'm going to have an arrow up to B from the empty set. Okay, and then I'm not putting A or B above each other because neither of them contains the other as a subset. But when it comes to the next one, AB, so AB does contain both of B and A as subsets. So that's going to go above both of those ones. And then I don't need to draw a line from that down to the empty set because that is taken care of by the transitivity of the Hasse diagram. Okay, so any lines that would be implied by transitivity, you do not have to draw them in the Hasse diagram. In other words, if I can go up from the empty set to B and then all the way up to AB, then I don't need to draw a line directly from the empty set to AB. Okay, so my next one is AC. So I'm going to put that one above A, but not above anything else. Since I haven't got C anywhere else yet, that just contains A as a subset. Then for ABC, that is going to contain AC and AB, as well as B and A as subsets. But I can just put that above AB and AC, and then it'll get A and B by transitivity. Okay, and then the last one is going to be ABCD, so that is going to go above ABC. Okay, so if you look at this completed diagram here, you see that if you start at any point and you are able to move up continuously up along a little chain to any other point, then you should be getting larger and larger sets the whole time. So wherever you start at should be a subset of the next place that you're able to move up to. And yeah, that's that one. Okay, so let's do one of these with the divisibility relationship. So we're going to say that A is less than or equal to B if A divides B. Okay, so again, I'm going to start with the one that divides the most other numbers, which is the number 1 that divides all of the other numbers. So I'm going to put 1 at the bottom, and then 98 will be at the top probably. So then let's see, 2. So 1 definitely divides 2, so I'm going to put 2 over there. But then 7, 2 does not divide 7, so 2 and 7 are not comparable under this partial order. So 2 doesn't divide 7, and 7 doesn't divide 2, so neither of them goes above each other. But then 14 does go above both of those, because 2 divides 14 and 7 divides 14. Okay, and then 49. So 49 is divisible by 7, but not by 2 and not by 14, because those are even. So 49 can just go above 7, like this. And then 98, so 98 is actually divisible by 49, and it's also divisible by 2, so it's also divisible by 14. So 98 is going to go right here. I'll put that above 49 and above 14, and then it's also above everything else by transitivity. So that's it. Okay, let's look at the last one. So this one is on ordered pairs, and the ordered pair partial order is going to be when the first coordinate here is less than the first coordinate in the second pair, and the second coordinate in the first pair is less than the second coordinate in the second pair. So you have the less than or equal relationship in both cases for both coordinates. Okay, so let's see, what can I put at the bottom here? I guess I'll start with 0, 1. So let's see, I'm going to put 0, 1 there. Now 1, 0 is not going to be above that, so I guess I'm going to have to put 1, 0 over here to the side. Okay, now 1, 1 should be above both of those, because 1 is greater than or equal to 1, and 1 is also greater than or equal to so if you look at the coordinates here, this first 1 is greater than or equal to the first coordinates of both of the lower points there, and then the second coordinate of 1 is greater than or equal to the second coordinates of both of those points there. And then let's see, 1, 2, and 2, 1. So 1, 2, and 2, 1 are both going to be above 1, 1, but neither of them is above each other. So I guess I'm making like a little X here, like this. So this is going to be 1, 2, and this is going to be 2, 1. It doesn't really matter which order you put them on from left to right. They just both need to be above 1, 1, and neither of them should be above each other. Okay, so that is that. Okay, that's it for this part of the video. Go to the next video for the rest of the solutions.